In this video, we're going to take a look at some important applications of the cross product vector. In particular, we're going to see that we can use the cross product to determine the area of both parallelograms and triangles in space. We'll use it to compute torque, the rotational effect of a force, and we'll be able to use it to examine whether or not certain points are collinear. We discussed in the video where we defined the cross product the idea that its magnitude defined the area of a parallelogram, but we haven't really explored why that's the case. So let's take a look at why that might be the case. So imagine we have two vectors. We know that if they live in three-dimensional space that they define a plane. So we're just going to put them in a plane here when we draw them. So here's our vector v, so that this length here is going to be the magnitude of v. And if we draw some other vector w, then the length of this is the magnitude of w. The parallelogram we're talking about is the one where if we were to make a copy of v parallel to itself and a copy of w parallel to it, we would get this parallelogram here. Now we have to remember some basic geometry. The area of a parallelogram is the base times the height, where the height is perpendicular to the base. So what we can do is we can drop a height right here, perpendicular to our base. We'll call that h. Then we have this angle here, theta, which is the angle between our two vectors v and w. We know from trigonometry that the sine of theta is opposite over hypotenuse, so that's h over the magnitude of w. Rearranging that, we get that h is equal to the magnitude of w times the sine of theta. Plugging that into our area formula, our area is going to be the base, which is the magnitude of v, times the height, which is the magnitude of w, times the sine of theta. But we know from previous videos that this quantity here is just the magnitude of the cross product of v and w. The triangle works almost identically. So for a triangle, see, I'm going to use a different color. I'll do the triangle over here. We have our vectors again, v and w, so that two sides of our triangle have length, the magnitude of v and the magnitude of w. We'll connect those to make our triangle. But again, the area of a triangle is going to be 1/2 the base times height. So if I pick v to be my base, my height is going to be perpendicular to the base. Again, over here we have our angle, theta. So we see again that h is going to be equal to the magnitude of w times the sine of theta. Same reasoning we used in our parallelogram, so that our area then is 1/2 the magnitude of v times the magnitude of w times the sine of theta, which is 1/2 the magnitude of the cross product of those two vectors. So area is one of our applications. Torque is going to be another. So let's talk about what torque is. So imagine applying a force to a particular point that's at the head of a vector. So something like turning a screwdriver or closing a door, where we have some rotational effect, the door on its hinges or the screw being turned. So the torque is going to measure, or it's going to be a vector that indicates the twisting effect that our force has. And there's got to be some point 0 or O at the head of our vector r. That is the point where the torque is creating the twisting. So we're going to define the torque to be the cross product of the vector r times the vector f. So r, again, is the vector along which we're applying our force. So in the two examples I gave, it would be your screwdriver or it would be the door itself. And then the F is the force that you're actually applying. It follows then from this definition that if theta is the angle between R and F, then the magnitude of the torque is going to be the magnitude of R times the magnitude of F times the sine of theta. If you think about what sine does as an angle increases, think about the sine of theta from 0 to 90. It's increasing from 0 all the way up to 1. The sine is increasing, which means that as the angle of our force approaches perpendicular, approaches 90 degrees, our torque, the magnitude of our torque, is getting stronger and stronger. Let's take a look at some examples. We'll start off with an area example. So here we have the vectors 2, 1, 0 and 1, 3, negative 1, and we want to find the area of the parallelogram that they span. So I'm not good at drawing in 3 dimensions. I'm not going to attempt to draw those 3-dimensionally, but we know that the area of this is going to be the same as the magnitude of their cross product. And so we'll just take the cross product and then we'll take the magnitude of that. So I'm going to have a lot of straight lines here to indicate I'm taking the magnitude of the determinant, which is going to give us a vector 2, 1, 0 and 1, 3, negative 1. So I'm going to just work on the cross product itself here, and we'll do the magnitude second. So this is going to be the determinant of the matrix 1, 3, 0, negative 1 times I minus the matrix, the determinant of the matrix 2, 1, 0, nope, that's a negative 1 times J plus the determinant of the matrix 2, 1, 0, negative 1. Nope, got that wrong. This should be 1 and 3 times K, which is going to be negative 1 minus 0 times I minus negative 2 minus 0 times J plus 6 minus 1 times K, which is negative 1I plus 2J plus 5K. So our cross product is the vector negative 1, 2, 5. The magnitude of the cross product is then the square root of 1 plus 4 plus 25, which is the square root of 30, which does not have any perfect squares that divide it. So we just let it be. The square root of 30 is the area of our parallelogram. We don't know what those units are, so we'll just say units squared. All right, let's try a torque problem now. So we're going to apply a force of 20 newtons to a 0.25 meter long wrench, which is attached to a bolt perpendicular to the bolt. So here's where we're going to start to wish that I could draw anything. I'm absolutely useless artistically, but here's my bolt, and my wrench is attached to it this way. So this is my wrench. It's an excellent depiction of a wrench. Use your imagination. And the wrench is 0.25 meters long. And we're going to apply some force to that wrench. So we have a force vector that's being applied at an angle of 45 degrees to the wrench. So this is 45 degrees here, and this is our force. And we want to know the magnitude of the torque. The magnitude of the torque. So we don't actually even need to compute the torque vector here because we have a formula. We know that the magnitude, we use the letter tau. That's what that fancy T is. The tau for torque is going to be the magnitude of R. We'll talk about what R is in a second, times the magnitude of force times the angle between them. Well, R here is, we should maybe call it W. This is going to be our wrench. This is the length along which our force is applied. So it's our wrench. F is our force. So the magnitude of R is the length of the wrench. So this is 0.25. The force is 20 newtons. So this is in meters, and this is in newtons. And then the sine of theta, well, theta is our 45 degree angle. So we get 20 times 0.25 is 5. The sine of theta is the square root of 2 over 2. And so the magnitude of our torque is 5 square roots over 2, 5 square roots of 2 divided by 2, and that is in Newton meters, which is the same thing as a joule. So the magnitude of our torque is 5 root 2 over 2 joules. All right, let's try another one in which I fear, again, we will despair over my inability to draw anything realistic looking. But here we have a set of caliper brakes exerting a force on the rim of a bicycle wheel. And it creates a frictional force of 40 newtons, that should say newtons in there, perpendicular to the radius of the wheel. Our wheel has a radius of 33 centimeters, and we want to find the magnitude and direction of the torque. So I'm going to attempt to draw a wheel. Maybe my technology will allow me to make a fairly round circle. That's good. Okay, now I'm going to put my caliper here at the top of my wheel. Oops. There's my caliper. The radius, we're acting on the entire axis or axle of the wheel. So our vector r is going to be actually twice the radius. So r is, the magnitude of r is going to be 66 centimeters, which we're going to write as 0.66 meters. I'm converting to meters because we know our forces are going to be measured in Newton meters. So we need everything in meters. And then our force, the frictional force, is acting on the rim of the bicycle here we have a 40 newtons is the magnitude of that force. And it's perpendicular, so the angle between these guys is 90 degrees, or pi over 2 radians if you choose that. So we know automatically that the magnitude of our torque is the magnitude of r times the magnitude of f times the sine of 90 degrees, which is 1. So we just get the magnitude of r times the magnitude of f. So we're going to have 0.66 times 40, which is, I believe, about 26.4. Let me verify that. 40 times 0.66. Yeah, 26.4. And that is, we're going to measure that. Our units are Newton meters. Now let's think about the direction of this. We could use the right-hand rule. If we point your hand down and then curve your fingers towards the other vector, we can do that, but let's do it mathematically. Let's actually compute. Let's compute our vector tau, and we'll see very easily then from its formulation what direction it's pointing. So we're going to look at r cross f. We're going to write the vector r. Let's imagine we need a coordinate system here. So I'm going to draw in my coordinate axes in gray here. So this is my I-axis. This is my J-axis, my K-axis. You have to imagine that extending out in 3D. There's K. So I can write r. My vector r is going to be the vector, it's pointing downward along the J-axis. So it is the vector 0, negative 0.660. My force vector is acting only in the direction of I, so it is going to be 40, 0, 0. So when we cross those, we're going to get, it's going to be actually very simple to compute because of all the zeros. So we have 0, negative 0.660, and 40, 0, 0. So we get 0 times I, because 66 or 0.66 times 0 minus 0, we get 0i, and then we're also going to get 0j, and then we're going to get 40 times negative 0.66k, so we get negative 26.4k, and we can see again easily from that. So our torque vector is the vector 0, 0, negative 26.4. So clearly its magnitude is positive 26.4, which we already saw, and its direction is in the negative. It's in the direction of the negative k axis. Add one more application that involves the cross product, we're going to determine if these 3 points are collinear. And so if we can relate this to the idea of area, first of all. So if we think about this, if we look at the vectors AB, which is going to be the vector 3 minus 1, 1 minus 0, and negative 1 minus 2, and we look at the vector AC, then that would be the vector 2 minus 1, 4 minus 0, 0 minus 2. If these are not collinear, then they can form a triangle. We can think about the triangle ABC with those 2 vectors as its side. And then if they're not collinear, then the area of that triangle would have to be greater than 0. Similarly, if they're not collinear, then that would mean that the vectors are not parallel. Both of those tell us that if they aren't collinear, I'm going to call this vector B for shorthand because I'm lazy, then B cross C is, the magnitude of that is not 0. The flip side of that is that if they are collinear, then the magnitude of the cross product would have to be 0. So a quick test for collinearity is to look at the cross product and determine is it 0 or not. So let's look at that cross product. So we're going to look at B cross C, and that is going to be the vector we get from this determinant. So I'm going to do 1 times negative 2, which is negative 2, minus negative 3 times 4, which is negative 12, so negative 2 plus 12 times I, minus, and then 2 times negative 2, minus negative 3 times 1, so plus 3 times j. We can already tell that this is a non-zero vector, which means it's going to have non-zero magnitude. And then k would do 2 times 4 is 8 minus 1 times k. And so we get 10i, what's that, negative 1, so plus j plus 7k as our vector. So 10, 1, 7. And the magnitude of B cross C is clearly not 0, which means that these 3 points are not collinear. There's not one single line that will contain all 3 of those points. All right, summarizing what we've seen here in terms of applications, we know that the area of a parallelogram can be found by taking the cross product of 2 vectors that form its sides. Similarly, the area of a triangle is going to be 1/2 times the cross product of vectors that form 2 of its sides. We saw that we can determine if points are collinear by checking their cross product. So our rule is the points are collinear if and only if, that's what that weird little IFF stands for, the cross product of the vectors connecting them has to be 0. And then we also saw that we can compute torque, which is a vector that's going to indicate the amount of twisting action a particular force generates, by taking the cross product of the vector on which the force is acting times or crossed with the force vector itself. And up ahead, we're going to be examining equations for lines and planes in 3D. We'll look at normal vectors, and we'll also be looking at how we can compute distances to lines and planes from both points and other lines.